Okay, so that's why I'm repeating that again. I think it's not lecture 2, I think lecture 3. Okay, is my slide visible?
Yes, sir.
Yes,
Okay, okay, thank you. Okay, so this, okay, so we will today we will study on normal and alert system in a power system. Okay, actually, in this lecture, what we are doing is we'll try to find out whether the power system state is in the normal or alert, and then after identifying normal or alert, then we'll try to do a some control techniques or control measure. But if it is in normal, then no need to do any control. But if it is in the alert stage, we have to bring back to the normal stage. So in that we have to do a control. So that control we call it as a preventive control. Why we are calling preventive control is because from alert state, you know that it will enter to the emergency state. To prevent that, okay, to entering to the emergency state and then bringing back to the normal state, so that control is known as preventive control. Okay, so in this lecture you will be able to learn that different states in a power system, then schematic of security assessment procedure means how to carry out that, and then after knowing that the states, how to control that. Okay, that is preventive rescheduling of a generation. Okay, so now in earlier lecture or the earlier lecture we have learned about the static estimation and dynamic estimation, or static state estimation and dynamic state estimation. Okay, so now once, okay, so as an operator, if you know the static estimation of the power system variable, so power system variable means system variable like voltage, current and phase angular. Okay, so you can say from that also you can say that to some extent whether this is power system state is in the uh, normal or alert or a emergency or restorative or in extreme state and so on. Okay, but if we go, okay, in detail, so you will find very difficult to differentiate between normal and alert state. Just obtaining a static estimate data, state data, we will not be able to say a power system is in the normal state or alert state, because see in normal state you say everything is within the limit. Even in alert state we can say that you will get a power and everything in the normal state. Only if there is little bit disturbances it will enter to the emergency state. So that how we have to carry it out, so that one we will see in this lecture. Okay, so first knowing that static state estimation of the system variable, then we will check for normal, alert or emergency state. And then we can also use the dynamic state estimate information available, but this which already I have said last class that it will be very difficult for this system operator to utilize this data, because within a fraction of second, okay, it will lose the synchronism example, or within a second it will come back to the normal. Okay, in such case it will be very difficult for a system operator to carry out the corrective action. But this dynamic state information you will use for automatic control or protection strategies. Okay, if it is for automatic, then we will go for dynamic information. Okay, so in automatic, as soon as you, example, as soon as you lose system lose the synchronism, then within a second, so this automatic control will do a corrective action or preventive action. But whereas system operator will find very difficult to take a corrective action. So in such case, that's why you have seen most of the control system is automatic. But in our lecture today, we'll focus towards the static state estimation only. Okay, which means we'll not use the dynamic. Okay, but we will carry out the static state estimation. So now, if you find, okay, so if from this static state estimation data, if you find that all the system or all the equipment in the system are within the respective limit or within their limit, then we call that system could be in the normal or alert state. So that's why I said that it is very difficult. If it is within the, very difficult to differentiate between normal and alert state. If all the equipment in the system are within their limits, let's say voltage limit is within the limit, then I can say either normal or alert state, right? So it could be either normal or alert state. But if it is in normal state, we are not required to do any control. If it is in alert state, then we have to do a preventive control so that uh, it will not enter to the emergency state, and then it will bring back to the normal state. So now it is finding very difficult to differentiate if all the equipments, which means if a system can withstand a potential contingency, if there is fault because of tripping of a line or generator, then it does not violate any equipment limits, or it is not losing any stability, then we can say that the system is normal or secure state. This all you know, right? Even it is not losing any stability, so then we can say that it is in secure state, and such type of network communication, okay, without losing any supply to the customer or any load, we can call it as n-1 secure. And then if, okay, so next condition is if it is within the equipment limit but it is not secure, which means it is losing the stability, then we call it as insecure, or that is in the alert state. Okay, so this is a different between. Okay, so but how to differentiate between normal state and alert state? Even in the normal state, you will get the same power. Even in the alert state, you will get the same power. But you have to identify. How you will identify is carrying out these two tests. Okay, normal and alert state. You have to carry out these two tests or analysis. Then you will be able to, okay, after carrying out these two analysis or tests, so then you will be able to differentiate between the normal and alert state. Okay, so first analysis you have to carry it out is static security analysis. Means you are checking the equipment limit violation. So whether voltage limit is within this, power limit is within the or not. If it is that within that, then we can say that alert state or normal state, right? We can say that if it is within the limit, then we can say it is either alert or normal state. And then if you carried out the dynamic security analysis, actually, so when we talk about the dynamic security analysis, we are checking for the stability of the system, which means if there is little bit of a disturbances, so stability of system will be or it will not be in the stable condition, then we can say that it is in the alert state. Okay, if it is not changing the stability of the system, then we can call it as a normal state. By carrying out this static security analysis, you will not be able to differentiate between normal and alert state. This is carried out just to find out whether it is violating the equipment limit or not. If it is not violating, then it will be in the normal state. If it violates, then it will not be in the alert state also. It will directly jump to the uh, emergency state, because if it violates the equipment limits, definitely it will violate the stability of the system. So if it violates the stability of system, it both, okay, so it will violating the both the condition, so then it will enter to the emergency state. Okay, so in dynamic security, so we are involving or checking the stability of the system, and if there is a, okay, if there is little bit of disturbances, and then if it is not in the stable system, then we can call it as it will be in the alert state, which means little bit of disturbances, it will enter to the emergency state. So in such states, we have to carry out the control. That control is known as a preventive control, which will bring back to the normal state. Okay, so this one I have explained earlier, but what you can do is you have to see carry out these two tests, and then if your equipment limit is within the limit or it is not violating the equipment limit, and then when you check or when you carry out the dynamic security analysis, it is the system is stable, then it will be in the normal state. In this normal state, no need to carry out any control, right? But if you wish, or if the system has a flexibility, you can also control, or we can also try to do some minor changes like real and reactive power changes or scheduling. Okay, so you can try to do, if system has a flexibility, you can carry out the real and reactive power scheduling. But where you are doing is, if your cost of the electricity or the cost is very high, and if you want try to reduce this cost so that you want to make your energy cheaper, then from economic perspective you can try to reschedule that if flexibility exists. Okay, in some system in normal you will not have any flexibility to adjust, but if there's flexibility to adjust, then you can try to do rescheduling of real and reactive power from the economic perspective. So when you do that minor changes, you have to take note of it, so it should not bring the system out of secure state, or it should not enter to the alert states when you do these minor changes. So it should not enter to the uh, alert state. Okay, so why you are doing these minor changes is from economic perspective only. So just thinking that your energy is costlier than compared to others, so you try to do some minor changes in real and reactive scheduling. But if flexibility exists only, okay. But if there is no flexibility, then no need to do it because it is already in the normal state. Okay, just we want to make it cheaper, so then we may do that. Okay, but if it is in the alert state or insecure state, then as an operator we have to carry out the real or reactive power rescheduling. Okay, so what that real or reactive power rescheduling is known as preventive control. Okay, so if somebody asks when you will do a preventive control in the power system, so don't say that we will do in the normal state. Even normal state we can do, but normally we will say that if the power system state is in the alert state, which means we are giving some warning, right? In alert state, we are giving some warning that if there is a little bit of disturbances, then it will enter to the emergency state or in extreme state. So in such case, we have to carry out the preventive control. So now when we do that preventive control or rescheduling of real or reactive power, so what do you have? You are trying security, means you are trying to bring back to the stability, and then already in alert state that all the equipment limit will be the within the limits. Okay, but only thing is your stability is disturbed, so you are trying to bring back or improve the security. But when you carry it out, there is no option. So when you do such thing, higher cost may be there. Okay, may result in the higher cost because sometimes this cheaper generator may have to back down. Okay, when you do this real and reactive power scheduling, sometimes you may have to shut down the cheaper generator and then you have to incorporate the generator which is costlier one. But there is no option, because if you don't do this, then it will enter to the emergency and then in extreme state, which means so your blackout will happen. So but cost will improve, uh, cost will increase, but there is no option for improving the security. We have to bear this cost. Okay, that when we are doing is we are doing when it is in the alert stage. Okay, this is just a schematic procedure of a security assessment. What you can do is, first, using this static data acquisition, you will collect the data, voltage, power, okay, all raw measurement from the remote measurement or from remote area. Okay, so you'll try to collect that data. Example, uh, last time also I have explained, in Bhutan we have BPSO, Bhutan Power System Operator. This will collect all this voltage, power, everything data from the Chuka, Tala, then even Kurichu. Now it has been Mangdichu is also integrated there, Mangdichu, Dagachu, and then all he will collect this voltage, power, and then all. Okay, after that what they will do is, so they will try to carry out the static state estimation. Means why we are doing this static state estimation is, so they want to see the operating condition, whether the power system is in the normal, alert, or emergency state. Okay, just carried out that. But I said that it will be very difficult to say that whether the power system is in the normal or alert state. So to identify that, what you have to do is, so you have to carry out these two analysis: static or dynamic security analysis. Static, you are carrying out to find out whether the equipment limit is violated or not. Then in dynamic, you have to see that whether the stability has been violated or not. Okay, so then based on these two analysis, you will be able to identify normal state or alert state. Okay, if it is in normal state, what you can do is, no need to do any control. But if there is some flexibility, if your generation is costlier, you just want to reduce that cost, you can do some minor rescheduling of real and reactive power. But when you do that, you have to take note that it should not bring the system to insecure state. Okay. Then if it is in the alert state, so let's assume that when you carried out this static and dynamic security analysis, so you have found out that it is in the alert state. So alert state means little bit of disturbances, it will lose this stability, which means it will enter to the emergency or directly to the in extreme. So in such case, you have to do a control. So that control is known as preventive control. How you will do is, you have to carry out the real or reactive power scheduling. So that is known as security constraint optimal power flow. Okay, so in this step, so sometime your generation cost may increase because there's no option, right? Because what we have to do is, cheaper generator may have to be back down or shut down, and we may have to uh, uh, we may have to adjust from the costlier generation. Okay, there is no option, but what you have to do is, for improving the security, we may have to bear this. If you are not trying to improve the security, okay, if you think that it is very costly and you are not carrying out the preventive control, what it will happen is, there is high chances that your system will enter to emergency or in extreme state, and complete blackout may happen. So instead of not having a power, then let better to pay a little bit higher, right? In such case, okay, this is how we carried out the schematic of a security assessment procedure. Okay, now with example we will carry it out. Okay, so in this example we just consider simple example. There is two generator A and B, and then there is one load which we have to feed from these two generators. And then to feed that, we have given all line parameter. Okay, line parameter, and then there is two line from A to C, and then in between generator, so we have to share this, right? So A and B, and then from B to C we will feed to the load. Okay, and then there are many conditions to be fulfill, but in our example we'll only see this one, transmission line limit only. So in unit 1 we have to study that transmission line limit should be 1500 megawatt, which means it should not increase more than this. If it is more than the 1500 megawatt, then we can say that that line is overloaded, means, okay, so it will not be stable. Okay, so now this is just a uh, example scenario we are considering. Okay, so we'll consider only the thermal limits. Actually that 1500 is a thermal limit. Okay, so thermal limit of all the lines are equal, and then dictate the power flow should not exceed. Okay, so thermal limit of this all transmission line will be same, and then power flow in this line should not exceed 1500 megawatt. Okay, if it exceeds, then it will be a uh, overloaded. Okay, so which means this is just a scenario I'm creating. Okay, so now with case by case we'll see. Now case 1 or operating condition 1. So let's assume that generator 1 is generating 1500 megawatt, and then 2 is generating 750 megawatt. Okay, in this case, just okay, so you can take example also. Okay, here since I have given 1500 and 750, I'm not giving the real example. So sometimes you can carry out this tala one and then chuka, and then you try to see that load, and then you can adjust that. So scenario you can create like this. This is a general one. We are assuming that generator one is generating 1500 megawatt. Why I'm not giving Tala and Chuka example is Tala is not generating 1500, Chuka is not generating 750. So that's why I'm not giving, but you can create your own scenario. Okay, so Tala here 1020, Chuka, and then you try to see load and where vary that. Okay, but here for your understanding purpose and simplicity, so I've just given that 1500 megawatt is generating by generator A, and the generator B generating 750 megawatt. Okay, and then we know that thermal line condition is all lines should not exceed the 1500 megawatt. And then load we have to feed is 2250 megawatt. Okay, just assumption we have make it. And then we assume that these two generator exchange the power of 187.5 megawatt. Okay, we this between these two generator, okay, it is exchanging 187.5 megawatt power, okay, between these two. Then remaining, so from 1500 megawatt, so remaining power will flow in this line A and AC. Okay, remaining power, there are two transmission line, so and then impedance also equal. So now what you can do is, so just divide it by 2. So you will get each line will carry 656.25 megawatt. Okay, which means 1500 megawatt minus 187.5, you will get divided by 2. So you will get each line will carry 656.25 megawatt. And then here from you have shared this, and it has to transmit to the load, which means 750 plus 187. So you will get 937.5 megawatt. Okay, 937.5 megawatt. And then if you observe this carefully in operating condition 1, see here, it is not exceeding 1500 megawatt. Okay, it's not exceeding 1500 megawatt. So in such case, what you have to do is no need of any control, right? It is within the limit, it is not exceeding. This line AC is not overloaded, it is within the limit. Even BC is within the limit, even AB is within the limit, which means there is no overload. Okay, means within the limit, this condition. But let's try to see if there is some problem at one line AC. There are two line AC, but if there is one problem at the line AC, okay. Now, if there is one line AC, still in this line between, okay, there is one problem in the line AC, and then still within this it can carry 1500 megawatt. So now we can adjust here, right? So now let's assume that when there is a problem in one line between the AC, so now between two generator, so we can share the power of 450 megawatt. So now you just do that, 1500 minus 450. So you will get this line is 1050 megawatt. And here generate B is generating 750. So if you add up 1200, and the still total load will be 2250. We are supplying the total load, required load. And then this transmission line is not overloaded. All transmission line is not overloaded. Even if there is some problem in one transmission line between AC, so still this operating state or operating condition is in the normal state. Okay, which one can verify losses of any one line. Okay, so one line will not cause any of the remaining line to be overloaded. Okay, so which means please when you carried out this for your understanding purpose, so please don't try to lose one line between A and B. Okay, if you lose this line A and B, so you will not be able to supply 2250 megawatt. Okay, so in this example, just to show that the line is within the normal state, so we have carried out this, okay, these two line, but one line has been, there is some problem or one line has been lost. Okay, but if one line is lost also, now we can see that you will not find that any line is overloaded when you supply the required load 2250 megawatt. Okay, so which means it is in the normal state. This is case one. Okay, another case, you can create your own case and then you try to understand that. Okay, case two is, so now in case two we'll try to see that generator B is sorry, A is generating 2000 megawatt, B is generating 1000 megawatt, and then total load we have to supply is 3000 megawatt. Okay, 2000 plus 1000. Okay, so 3000 megawatt. And then what we are doing is, so now in this two, between two generator, it is sharing 250 megawatt. Okay, so if it share 250 megawatt, then remaining 2000 minus 250 divided by 2, so each line will get 875 megawatt. Okay, 875 megawatt. And then you will get here line BC equal to 1020 megawatt, and then you will be able to supply the 3000 megawatt. If you add up, it will get 3000 megawatt. Okay, so this is operating condition 2 and a scenario we have created. But let's assume that one line between AC has been lost. Okay, one line between AC has been lost, and if it lost, so now what we are doing is we are trying to adjust such that between these two lines 600 megawatt is sharing. Okay, so between these two generators 600 megawatt, and then generator one already is generating 1000 megawatt. So if you add up, it's coming 1600 megawatt. And then here between line AC, so if you minus 600 from the 2000, you will get 1400 megawatt. So now total load you are supplying is still 3000 only. Okay, you are fulfilling the total demand, but problem